So from the three differential equations we derived for velocity and acceleration above, we can use those to derive other equations of kinematic equations of motion. For example, suppose you're in a situation and you need an equation that describes velocity as a function of time. Then which equation do you use? Well, you look over here and you see that it depends what you have as variables. If you have acceleration in your formula, you'll maybe want to use this equation. So the second equation. So let's do that. So let's take acceleration equals dv dt and solve it for v. So separate the variables. So the integral of a dt equals the integral dv. And let's go from 0, or let's call this t0 to be general, t0 to t, and we'll go from v0 to v. So this gives us the acceleration times t evaluated from t0 to t equals velocity evaluated from v0 to v. Now notice here I say this is acceleration times this. Acceleration, actually here you want to assume it's constant. Otherwise we'll need a relationship for acceleration as a function of t. Okay, so let's look at this. This is a, let's say again that t0 equals 0, and this is then a t equals v minus v0. So solving for v equals at minus v0. And that's a situation where t equals 0. t0 equals 0. Okay. Oops. How did that even happen? Okay, so let's find an equation for position as a function of time. Let's assume here that, again, maybe t0 equals 0, that we have a v0 and we have a constant acceleration. So constant initial velocity and a constant acceleration. Okay, well, let's use the relationship dx dt equals v here, and we'll go ahead and go from x0 to x of dx equals separation of variables again, the integral of v0 to v of v dt. Actually, this is dt here, so we're going to go from t0 equals 0 to t. Well, here v is not constant necessarily, and what we can do is we can use the relationship that we got from above. If v equals at minus v0, notice that's v is a function of t in that relationship. We can plug that in to our equation, and over here on the left we're going to end up with x minus x0 equals, let's go ahead and plug this in and solve it this way, 0 to t of at minus v0 dt. Notice v0 and a are constants, so this equals a t squared over 2 minus v0t, evaluated from 0 to t, which will give us, substituting in t here, we're going to just get a t squared over 2 minus v0t. So x, isolating x then, equals a t squared over 2 minus v0t plus x 0. Finally, let's look at one more situation. Let's do the velocity as function of distance. And again, let's just assume that acceleration equals constant, not 0, but a constant value. Then in that situation, let's use a equals v dv ds. So our separation of variables results in a ds equals v dv. Again, acceleration, assuming constant, from, I may as well call this x since I've been doing that above. x0 to x dx equals the integral v0 to v of v dv. So we get a x evaluated from x0 to x equals v squared over 2 evaluated from v0 to v. So a x minus a x0 equals v squared over 2 minus v0 squared over 2. Solving this for v, we can multiply both sides by 2. Gives us 2. Let's pull the a out here. 2a x minus x0 plus v0 squared equals v squared. Now we could take the square root of both sides to solve this if we needed to. Okay, we got a rocket engine that fails at 40 meters. Find the maximum height. That's part A of this. Well, when a rocket engine stops, the rocket will continue upwards until gravity slows it down at some point. Then it'll turn around and fall back to Earth. So in this situation, we can assume gravity equals, since this is meters, let's use the SI units and go with 9.81 meters per second squared as our acceleration. Also in this relationship, we have another quantity given in the problem. I'll write it in blue with v0 equals, well, at situation 40 meters and V0 at 40 meters is currently going 75 meters per second. So here we're looking for a distance. We're given constant acceleration. We're given a value of V0. If we had a value of V, we could use this relationship. V acceleration equals V dV dx, and that will result in this differential equation where and again, let's put this as x, where x starts at 40 meters and goes to some height h here, and v starts at v0 equals 75, and it goes to some v at this height. Well, in order for this to stop and start falling back down, v at that height has to be equal to 0. So we have everything we need in this relationship, and we can solve for h. And here's the solution to these integrals. And let's put in values. So a equals 9.81. H minus 40 here equals 75 over 2 squared, minus, or 0 minus 75 over 2 squared. Also, since we're taking this direction as our positive, gravity is actually a negative, so let's put negative in this relationship. Solving for h gives us this relationship, and when we throw that into a calculator, we end up with, say, 326.7 meters. Meters because the second squareds cancel out and one of the squares cancel out. Now notice that's h measured from this datum line, because we have included this 40 in our relationship. So we can solve this in a couple ways. If we're starting, if we think of this, one way to do this is to think of this as at the top, we have a situation where, again, using the red line as datum, where h naught that we're starting at equals 326.7 meters. We have our initial velocity up there is 0. It's stopped and is turning around. Our final velocity is, we don't know that. That's going to happen when we hit the ground. And our final h is going to be 0. That's also when we hit the ground. H is the distance that we are in the air. So again, a equals minus 9.81 meters per second squared. So let's set it up. So here is our integrals to solve, and now x0 starts at 0 and ends up at minus 327. We start at 0 for v0 here. Let's call this v0 equals 0, and v final equals minus, well, this equals minus v final. So we end up with this equation, and then putting in the results, then putting the values in, our initial conditions, and our final velocity equals, oops, made a mistake here. What we have for v0 is not 0, it actually was minus 75. No, wait, there is no mistake. I started from a height of the 327. Okay, and then so our final answer is minus 80 meters per second.